Okay, good morning. From macrocycles and calyxarines, let me now introduce another supramolecular synthon that is called cryptands. Okay, cryptands. In fact, cryptand molecules are the first introduced by Jean-Marie Lehn, and he was the idea behind that for complexing, effective complexing of alkali metal ions. You already know that alkali metal ions can be complexed by crown ethers. So, let me draw a crown ether, a cartoon of a crown ether. Here is a crown ether, okay? 15 crown 5, say this is a crown ether, and this 15 crown 5 can accept a sodium ion inside. It can accept a sodium ion inside, all right. But what happens, as I told you previously while discussing Lariat ethers, that reagents can react it with this metal ion from top and from bottom. So, the metal ion even inside this cavity, macrocyclic cavity, is susceptible to attack by reagents from outside. So, Lehn first envisaged that if we have system where the metal ion will be completely surrounded by these aromatics, then what happens? So, from this 2D he went to 3D. So, let me write his molecule. He first made this molecule. Okay. So, he said that if we have a molecule like this, then what happened? Then I can put a metal ion inside, and that is completely surrounded from all directions. So, it is an isolated metal ion is now isolated, okay, inside the cavity of this molecule, and he told these molecules are cryptands. So, this actually is the, you can say that, beginning of supramolecular chemistry as a coherent subject. Supramolecular compounds are there for eternity, okay, because in biology all supramolecular compounds are there, supramolecular interactions will always be there. But supramolecular chemistry as a subject, he introduced this term as a coherent subject, and his idea was to make molecules of this kind, because the metal ion, once it gets in, then it is completely surrounded by this structure, so that it will not be attacked by outside reagents, and it will be a very stable compound. And when the metal ion is inside, it is known as cryptate. A metal ion inside that will known as cryptate, okay, and this is called cryptand. Without a metal, this structure, organic molecule, is called cryptand, and this is a cryptate. Now, beauty of this molecule is that we can put these donor atoms. Here are oxygen donors, 6 ethereal oxygen donors. So, these are this is called a bridge. Structurally, let me say this we called a bridge. So, there are 3 bridges and this one is bridge head. Bridge head, this one. So, here is an example, with that nitrogen bridge head, and in bridges the donors are all ethereal oxygens. Okay. So, now let us see how we can vary. We can vary the bridges. That means, I can replace these ethereals by secondary amines or sulfurs or phosphorus donors. I can vary through synthesis. Synthesis of these compounds are very complicated. I am coming to that later, but now right now I am discussing all these variations and etc. So, I can vary these donors. I can put this donor at strategic position for optimum binding of a metal ion. It can not only accept a metal ion, it can accept an anion, a neutral molecule and so on. It can accept a metal ion along with an anion or a neutral molecule. It can accept more than one metal ions. It can accept several water molecules connected. So, all are known. So, this is a very versatile ligand, if you call it. So, this bridge, there are 3 bridges and 2 bridge heads, and this we will call laterally symmetric. Why this is laterally symmetric? It is obvious, is a symmetric structure, laterally symmetric. What will be a laterally non-symmetric? If I replace this oxygen, say I replace this oxygen with nitrogen, I can do that. I can put them with nitrogens, nitrogen, then it is laterally non-symmetric. Okay. So, these are some of these, and then I can put one as sulfur. I can do anything I like. I can do very versatile compounds. I can put sulfur here. Okay. Now, I can put bridgeheads as carbon. So, let me write some of these structures that I have written here. This was the first. Not only that, I can write, I can make okay, or here I can make a carbon bridgehead, sulfur, 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 amine, 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 let us put nitrogen here. can make this, or we can make, here I have made one aromatic, okay. Sulfur, 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 so anything I like I can make like this. Okay, this is not really good looking, let me make it little bit better looking. Okay. So, this way we can make many things, we can make both sides aromatics, we can make 3 aromatics. So, there is no dearth of, we can make, we can have double bond here or triple bond here, and this will vary. If you want to make, we can have aromatics here. So, we can vary rigidity of these molecules, and sometimes if you make say aromatics here or cyclohexane here, that means we call it organic skin. So, if you put a metal ion inside, I put a metal ion inside, this will be quite isolated if I increase the organic skin here. How? I put say cyclohexane, it will be soluble in I can put cyclohexane like this. You know what I mean. Okay. This could be aromatic, is easy. So, if you put a metal ion here, a metal ion here, metal ion is not soluble in organic solvents. Okay. A metal ion like say copper or say nickel like that, it will not be soluble in hexane. But if I have this cryptand, metal is inside the cryptand. So, it is surrounded by this hydrophobic moieties here, and so we call it organic skin. Organic skin is thick here, and that will dissolve this whole thing, this cryptate in say hexane or toluene like that. So, these are very important, can be important phase transfer catalysts. So, there are various properties we can extract from this cryptate formation, and these molecules are just marvelous. Okay. Now, I am not going to discuss their complexation properties as yet. So, as I told you that rigidity can be, so this is not a very rigid. How it can be rigid? If I make it this as aromatic, if I make it aromatic, then it will be rigid. Aromatics make this thing rigid, it can be rigid, and this rigidity can be varied, all right. Another thing is, and rigidity can be varied through this layer effect, and in layer effect is that its solubility also alters. We can put a metal ion in organic solvents of very low dielectric constant, like I said just hexane and all that, and it can transfer, it can be used in phase transfer. We will see some examples later, all right. Now, another thing is important, that these molecules can exist, these molecules can exist in three, let me draw a picture first, three conformations. Say I am drawing like this, this is one conformation, where my lone pairs on these bridgehead nitrogens are outside. This is one, we call it out out or XO conformation with respect to, it is XO with respect to these bridgeheads. Now, it can be XO endo, let me write endo 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 and XO. My endo looks really ugly, I will try to make it little bit better. Okay. So, this is 2 endo endo. Endo XO, XO. Here the lone pair is pointing inside, and then I will have both endo. Both endo endo. Both endo means the lone pairs are, both the lone pairs on the nitrogens are towards the cavity, inside the cavity. So, this is a very favored conformation for binding metal ions. Metal ions are Lewis acid, so they will require these lone pairs, and they can bind through these oxygens and through the, and also the to the nitrogens. So, there are 3 conformations possible with macrocyclic, macrobicyclic cryptan. These are known as macrobicyclic cryptans. So, these are all the structural aspects of cryptan, and as I go along, I will show you structural variation of these molecules and how they can be changed and what properties we can extract out of these systems, and how they are important in supramolecular chemistry, which will be quite obvious to you as we go along. All right. Now, I will talk to you about synthesis, how to synthesize these molecules. Before we do synthesis of this molecule, it has two aspects. One aspect is strategy. I will discuss strategy, and I will discuss methodology. So, we will discuss both strategical aspects and how the detailed methods of synthesis of this kind of molecules. All right. Okay, let me since we have still few more moments, let me discuss strategy. Strategy is F and F. These are functionality, that is linear organic molecules. We at each end there is a functionality, and they will combine to form a, it looks familiar to you because we discussed this while talking about macrocycles. And when you do that, then I will say another H and K, or even H and H, so it will bind. So, this one we will call it stepwise synthesis. Stepwise synthesis. This is called stepwise synthesis, and then see, we worked on cryptands for my research during my career, and we synthesized these molecules by this method, what I am showing you now. So, this is a tripodal unit, another tripodal unit, and you just join them. You get this tryptan, as simple as that. That is called tripodal coupling. Tripodal coupling. Tripodal coupling is the synthetic method we adopted first, and since then is all over the world is now being used. It is a very easy process. All right. Tripodal coupling is a very easy synthetic route for this kind of molecules. Another person who used cryptands by is called tripodal capping. Tripodal capping. I will show you here. So, this can be capped. This can be capped. Okay, this can be closed there, and there you use all of the in many cases you use template. So, templating we will not discuss. Another important is if you want to make very big, I want to make, so this is tripodal capping, let me write. Tripodal monocapping. Is a tripodal monocapping strategy. Now, I will talk about tripodal bis capping. Where you take okay, tripodal bis capping. Okay, tripodal monocapping, you can get a very rigid kind of cryptands, and tripodal bis capping is you can get get cryptands with a large, very large, long rather, by large I mean long, with a long cavity. Okay. We can get up to say 24 angstrom also. So, cavity can be really long, because this linear spacers we can vary, okay. And then we can it is very amazing, it is an amazing fact that this particular in the system we have 12 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At 12 points reactions is taking place, and it is reaction is going on as we want it. Now, how to bring about such a reaction? Earlier it was people thought that if we do like this 12 at 12 point interactions, we will get a very oligomeric products, and we cannot handle that oligomeric products, because this will not be good. We cannot isolate the product, but I will show you examples, real life examples. We did it. These compound, this and as well as here, as well as the tripodal coupling, that we can get yields pretty high, 40% and above. How to get that? So, there are stories. So, all those all those stories, and this synthetic we will talk about when stories will come into play when I discuss methodology also. So, therefore, in a nutshell, cryptands can be made by stepwise synthesis, and this is the original method adopted by Jean-Marie Lehn. Okay. This is a very versatile compound, versatile method, and here you can put different types of donor atoms in the bridges. So, it is a major advantage. However, at each step, from this step, at each step from here to here, we get the product along with oligomers. So, we have to purify by column chromatography and then take the pure product to the next level, and so on and so forth. All right. So, therefore, it is a very lengthy process, high dilution, tedious process. It can take a week also, but this is the original method. Still sometimes sporadically people use it, but the beauty of this is that we can get really asymmetric cryptands can be synthesized, which are very, very important also. And then okay, and then we have we have tripodal coupling. As I said, this was our original method we used, and now it is followed, now it is used very common, is very popular, because you have take two tripodal units and then couple them. That these functionality here and here at the end must react very fast, so that we can get the product without any minimum amount of side products. We can get that, and tripodal monocapping is like a tripod, and we can put a reactions, typical reactions, and then we can slowly one by one we can put say amine, we can put amine, and then these amines can be condensed with some alkyl halides and all that. All right. So, these kind of processes are known, and with a tripodal bis capping, here is a tripod, here is a tripod, and here is a linear chain. They all come, these 12 units, and then they form a long cryptands with long cavity. So, there are now almost several hundreds, several hundreds cryptands of different kinds of architectures are available today, and we make we can by order we can make any cryptands we want to do. Thank you very much for today.